As I said this morning, I sort of split up what I'm talking about on coupled ocean atmosphere systems kind of along the different time scales. So this was the slide I showed this morning and looked mainly in the lecture this morning on short and medium range timescales. This evening, I'm going to cover these three timescales. Don't worry, that doesn't mean it's going to be 3 times as long. I'm going to say a fairly limited amount about all these different timescales. As I said before, trying to link in with the ocean-related aspects of them where that's particularly relevant, and linking in with some of the themes we've already seen this week. So seasonal and decadal prediction, as I said, I'm by no means an expert on some of this, but hopefully I can give you a bit of a flavour for the general themes and principles. So it's generally considered as a sort of mixed initial and boundary value problem in this kind of seasonal decadal regime of the timescale. So when you're running very short weather predictions or ocean forecasts, you're mainly considering it as an initial value problem. Getting the initial conditions right is very important. On much longer timescales, so climate timescales, it's the forcing, things like anthropogenic emissions and aerosols which are driving the system, and other factors like solar variability. And seasonal and decadal is kind of somewhere in the middle. You've got a mixture of all these different factors going on. I think it's fair to say more and more of it is starting to be considered as an initial value problem now, and perhaps less of a force problem, particularly on the seasonal timescales. And sometimes when you hear people talk about seasonal forecasting being more of a force boundary value problem, that's looking at it from an atmosphere point of view. If you consider the ocean as outside your system, then the ocean providing the force boundary condition is that side of the problem. But if you consider the ocean as part of your system, then it's an initial value problem for the system as a whole. So these are a sort of schematic of some of the different elements of predictability in the climate system on different timescales. So the green items are aspects of the initialisation and how they influence predictability. So we've got things like the ocean circulation, the ocean meridional overturning circulation, heat content, for example, in the North Atlantic. I can't really read this very well from here, but things like ENSO, tropical ocean parameters, sea ice. And then on the forcing, the boundary condition sort of aspects, you've got things like solar variability that I've already mentioned, volcanic aerosols, of course, difficult to predict, but they can have a big impact on the system. And then the emissions, which to some extent, obviously, you can make assumptions about how those are going to change, but that's considered to be outside the system that we're looking at. So I'm going to go through those 3 timescales: seasonal, decadal, and then climate. And so here we're looking at providing sort of probabilistic forecasts of weather regimes and related impacts on a timescale, sort of roughly, I would say, sort of 3 to 12 months. That's probably 12 months is the kind of the longer end of what most people would consider for seasonal forecasting. But certainly the first sort of 2 or 3 months ahead, a winter ahead, for example, 3 to 12 months is the sort of timescales we're looking at. Most climate seasonal models are lower resolution than the kind of models we've been thinking about this morning for medium range, say perhaps sort of 50 kilometers for an atmosphere configuration, or sometimes lower than that, 1/4 of a degree for the ocean, or sometimes lower than that. A lot of models still 1 degree. Fabrice, I think, was asking a question about that after the ENSO talk yesterday. So a lot of seasonal forecast models, at least until recently, have been sort of 1 degree ocean and maybe 100-kilometer atmosphere, and they've kind of just shifted up the resolution as we've seen some benefits by doing that. as I've sort of hinted already, the atmosphere initial conditions are less important than for short range, but actually the other parts of the coupled system become more important. So particularly the land surface, the upper ocean, both in the tropics and in the North Atlantic, for example, and sea ice as well. And getting those initial conditions consistent isn't it as important as the sort of issues I was talking about before with things like initialisation shock. Most of those things will kind of adjust over the first week or two of your forecast, and by the time you're actually looking at a sort of 3-month seasonal forecast, they probably don't have much of an impact. That obviously you want to try and keep things as consistent as possible, but it's not as critical as for the sort of initial value forecast problem. And part of the seasonal forecasting methodology is that you usually need to run lots of historical forecasts, which I'll probably keep referring to as hindcasts. I try to avoid doing that, but I always slip into it. So these are kind of retrospective forecasts for dates in the past. And by running those, you can kind of calibrate the skill of, well, you can both assess the skill of your system, and you can also use those to calibrate your present day forecasts because of the inherent biases that you will have in your system, and I'll talk a bit more about those as well in a moment. We heard lots about ENSO yesterday afternoon, which thankfully means I don't need to say too much about it, but as Mike clearly explained to us, it's the main driver of predictability on seasonal timescales. And we're now starting to see that the dynamical seasonal forecast models, like the ones that I've outlined on the previous slide, can at least equal and start to outperform the statistical models, where we're just looking at statistical relationships between ENSO and the other teleconnections, for example. So if you like, the predictability sort of leaks out of the tropics via things like Rossby wave chains that Mike was mentioning as well. And then that can then impact things like the PNA and the PSA that we heard about yesterday, and also the North Atlantic Oscillation, which is the thing that I'm really going to focus on in some of the sort of new frontier aspects of seasonal forecast systems. I'll say a bit more about that on future slides, but that has a very big impact on European winters in particular. So if you've got a good seasonal forecasting system, you want good initialization. You want to get those ocean aspects, particularly in the initialization, right, and the sea ice. You want to couple model an underlying physical model, which is good. You want it to have a good representation of ENSO variability. You want it to be able to predict ENSO itself well. And as Mike said, that there's still a lot of difficulty doing that. But you want it at least to have a good representation of the tropical Pacific. And you then, if you're going to get ENSO right, you then want to get the mechanism by which that predictability of ENSO then kind of propagates into things like the NAO, and how that then influences the climate. And certainly for our models, it appears that the ENSO impact on the NAO, for example, that having a stratosphere in the model is an important part of that. So I'm going to explain a bit about the seasonal system at the UK Met Office. I'm afraid these slides, both for seasonal and decadal, are a bit sort of parochial, because that's the system that I know about. But similar results have been found in various other systems, and I think in many regards these systems are fairly world leading. So I think they give a good representation of what's going on at the new frontiers. I think we were one of the first systems to make that resolution change from sort of 1 degree ocean to 1/4 degree ocean, up to sort of 60-kilometer atmosphere rather than much lower resolution, and to use a fully coupled model, including, for example, sea ice components. So, as I say, this is what, for seasonal forecasting, we would consider to be high resolution in atmosphere and ocean, and also to have a well-resolved stratosphere. So we have 85 levels in the vertical going up right into the stratosphere. And it is the same model system that's used across timescales, so it's the same one that produces, well, that's at the core of our weakly coupled data assimilation system, for example. So some of that information is then repeated on that slide. The model itself gets called HadGem3 at times, and the scientific configuration of it gets called GC2. So I'll try to avoid using those things, but it may be that I mention them, and that's what I'm talking about if I do. As I said, these are probabilistic ensemble simulations. So this is a stochastic physics scheme to provide some perturbations in the atmosphere. And the initialization approach also uses a lagged ensemble to provide some initial condition uncertainty. So the way the system runs is that in our operational suite, we run 2 seasonal forecast members each day. And then we create products by pulling together the last 3 weeks of ensemble members. We also have some additional members for monthly forecasting, but I won't go too much into those now. But as I said, what we need to do is run a hindcast as well in order to assess the skill of our real-time system and to be able to calibrate it. So alongside these real-time members which run every day, we've got a 23-year hindcast which runs in real time. So we run 3 members for each of those 23 years for an equivalent date each week. And we need to, if we make any changes to the science or the sort of physical parameterizations in the model itself, then we need to be rerunning these hindcasts. But as I say, we do that in real time. Initialization, I've already said something about. So it's an uncoupled initialization, so an atmosphere analysis which just comes from our numerical weather prediction, degraded to a lower resolution for the seasonal forecast model. And the ocean and sea ice analysis is from our ocean-only foam analysis system. For the hindcast, of course, you need to be initializing the retrospective forecast as well, which is more difficult to do, particularly because we don't have an in-house Met Office atmosphere reanalysis. So we actually use ERA interim reanalysis for initializing the atmosphere and land surface, and we use ERA interim forcing for the ocean reanalysis that we run to initialize the ocean. That does create a bit of an inconsistency between the initial conditions that are being used for the hindcast, which is used to assess the skill of the system and to do the bias correction, compared to what's actually being run in real time. But we haven't come across any particular problems with that, and the ocean reanalysis with ERA interim forcing, for example, is very similar to the operational foam one. So that's a schematic which attempts to show how we run the system, but probably don't need to say too much more about that. So this is an example of how the bias is dealt with. So actually, all models tend to drift. So this is a Nino 4 SST region, and SSTs in the Nino 4 region, and you'll see that actually all the model, or the majority of the model members, are actually cooling quite considerably from the hindcast members. And so the hindcast climatology kind of looks something more like this, whereas the observed climatology is like that. So we do bias. Oh, hang on. So I hadn't checked out all these animations. So when you then get some forecast members like that, you know that actually it's really the difference between this kind of ensemble and the hindcast climatology, which is giving you the information about what you think ENSO is going to do. So that would be sort of calibrated to produce a forecast, something like that. So it's a relatively unsophisticated bias correction scheme, which means that it's really important to do the utmost you can to improve the underlying model so that you have as small as possible drifts and biases in the historical hindcasts, and you're doing less with the bias correction. For temperatures, it's relatively easy to do this kind of thing. For things like sea ice concentration, which is kind of either there or it's not, it can be more challenging to work out exactly how to do a bias correction. And then we assess the skill of the system in various ways using sort of reliability diagrams like this one, where you would hope that the lines kind of lay along the diagonal. So you'll see that actually a lot of our seasonal systems are not particularly good on many metrics, but they're certainly improving over time. So these kind of diagrams are really important in working out where we can trust the information we're getting from them in the different probability terciles, for example. So I've just kind of said that. We also look at things like relative operating characteristic scores. So in this case, a perfect model would kind of go kind of right the way around the edge here. And so actually you'll see that we're particularly in the kind of middle tercile, we're a long way from that. But for upper and higher and lower terciles, we're kind of getting a bit towards that direction. And as I say, it's useful information to know where we're doing well and where we're not. And that kind of information is also made available in maps that go alongside the seasonal products. We also look at things like anomaly correlations. So in this case, higher is better. And this is a comparison between our old system, which did have a lower resolution ocean and atmosphere, and our new higher resolution system. And again, you see improvements in anomaly correlations and some decreases in RMS errors for the Nino 3.4 SSTs we heard about yesterday. I think this was a reasonably helpful plot in the context of sort of questions about whether resolution helps ENSO. I mean, in some regards, I think we've seen in Met Office systems that going from a lower resolution atmosphere and ocean system to a higher one, we get the general patterns of ENSO SSTs better. We don't get quite so much of this kind of westward extension, and the general kind of central part of the warming pattern is better, but there's not that much in it, and of course that doesn't necessarily mean the predictability is better in the system. But it does seem like resolution is at least one factor in helping improve the representation of ENSO in our models. And we can also look at things like the teleconnections that Mike was talking to us about yesterday, and see that they match up pretty well between observations and forecasts for our Glossy 5 seasonal forecast system. So these are differences of precipitation globally for El Nino and La Nina. So I will say a bit more about the NAO, partly because it's very relevant for the European region, and that's where I live, and a number of the rest of you live. Apologies for those who don't. And partly because I think it is an area where there's been significant progress recently, and particularly in our Met Office system. So North Atlantic Oscillation, it's essentially the pressure difference between the Azores, which is typically a high pressure area, and the Icelandic low pressure. And I've already mentioned, I think, that the link between ENSO and the NAO is quite important. But other factors which are also important are the sea ice in the Kara Sea, the Atlantic sort of surface heat content in SSTs, and the quasi-biennial oscillation, or QBO. This is just a schematic of the NAO showing the two phases that it typically has. So this is the Azores high pressure and the Icelandic low pressure. In a positive phase, when this pressure difference is more extreme, you get more storms coming across the Atlantic, which tends to lead to a kind of wet and warm conditions over northern Europe. The opposite phase, negative phase, tends to give dry and cold winters in Northern Europe. And here we've just got some examples of the different factors which are involved. So the ones we've talked about already, so ENSO, that's indicating heat content in the operation, sea ice. This is a schematic of the quasi-biennial oscillation, so it's roughly 2-year periodicity. This is the MJO, which, as Mike mentioned, is quite important in all these things as well. And also volcanic and solar variability has some impact, although smaller than on decadal timescales. And I think the big sort of success of the Met Office seasonal forecast system has been the correlations that we've been able to find for forecasts of the winter NAO. So these are forecasts from November for the following winter, so December, January, February. So only just ahead. It's not a long way ahead, but found correlations of about 0.6 between our historical hindcast members and observations. And this was published actually a few years ago now, and since then we've found that doesn't seem to have been a fluke. That seems to have essentially continued in our real-time forecasts. And I think since then, a number of other centres have found similar results and got correlations of order sort of 0.6, which are much higher than the correlations that were seen before. One thing we've noted is that actually, and I'll come back to it later, the suggestion is that with more ensemble members, well, a lot more ensemble members, we could get a correlation of close to 0.8, but there's a very low signal-to-noise ratio, so you need a lot of ensemble members to sort of tease the signal out of the data. So where's that predictability coming from? Again, these are the same sort of list of factors that we looked at before, and it's quite helpful to put them in the context of what the observation suggests should be happening and how well the model's doing. So we know that a lot of that predictability comes from ENSO statistically, and the model shows very similar correlations between ENSO and NAO in terms of pattern and strength. It's perhaps less good for the North Atlantic SSTs and surface heat content. So broadly the same pattern of correlation, but much less strong. The sea ice is less good in our model. The pattern looks quite different there, and you're not seeing the same correlations. And the QBO is kind of well known as being something which models don't necessarily do so well, but there's some consistency between those patterns. So it seems like these four items combined are giving about 0.5 of the correlation that we're seeing, and it looks like the rest of it is coming from partly elements to do with the stratosphere and sudden stratospheric warmings. I'll just skip over those, I think, in the light of time. And other predictability coming via ENSO and via the tropical precipitation anomalies. So we know that there are correlations between El Nino giving negative NAO and Western Pacific rain giving positive NAO. And by looking at some of the Rossby wave trains from those different areas and the impact on the NAO, we can show that it seems like the tropical rainfall, and particularly in the Atlantic, is contributing quite a significant amount to the predictability of the NAO in our system. That's not to say that these, as with any correlations, there are always going to be years where things don't quite seem to work out, and in this case, 2004-05 was a kind of an obvious example where the correlation isn't very good. This is showing this issue with signal to noise ratio. So this is the 0.6 correlation we get for the North Atlantic Oscillation with our seasonal forecast system, and with ensemble members on the x-axis. So the suggestion is that if we had enough ensemble members going up from kind of 30 odd we have now to 80, we could get up to about 0.8 correlation. But there's something quite strange going on in the system, which I still find it hard to get my head around exactly what this means. But the skill rises very slowly with the ensemble size because the signal to noise ratio is low. And essentially what we're seeing is that the real world is more predictable than the model. So the model can do a better job at predicting the real world than it can at predicting itself, which seems quite sort of strange. It's hard to understand exactly what that means. But essentially it means that the members aren't kind of alternate realizations of the observations. And you might think that was just something to do with a problem with the spread in the ensemble, but it seems that's not the case. Actually, the spread in the model NAO and the variability in the observed NAO is actually quite similar. So we've been doing a whole load of tests to try and work out what's going on there. And these are the sort of things we've been looking at. We've been trying to work out whether it's something to do with tropical rainfall, whether it's something to do with the way the Rossby wave sources are working, something to do with the MJO, which is poor in a lot of our models, or something to do with the sea ice not being very good. We've also looked at increasing both atmospheric and ocean resolution, so we run a 12th degree ocean version of this system for a relatively limited number of cases, but all of those things showed little impact really in improving what was going on. And the only two things which seem to point to this being the cause of this low signal to noise ratio are the stochastic physics that's in the system, or at least the particular formulation of the stochastic physics, and also probably some issue with non-orographic gravity waves not being parametrized correctly in the system. So we're hoping that addressing those things will give us a much higher NAO correlation without having to run a huge ensemble. So I'll move on to Decadal now. And again, we're looking at probabilistic predictions. Timescale there, 1 to 20 years. I mean, our decadal system actually only runs out to 5 years most of the time. But some systems have been run for longer. Usually a sort of intermediate resolution, so similar to the seasonal system, and at the Met Office we actually use the same resolution system, so 50 kilometer atmosphere, quarter degree ocean, but again other systems might be lower. And we're getting this combination of long-term natural variability and externally forced changes, as well as the impact of the initial conditions. So kind of it sort of makes sense that as you go to longer timescales, it's the deeper ocean initial conditions which become more important, and the impact they have on initializing the variability in the ocean in the correct state, so the overturning circulation, for example. But aerosols, greenhouse gases, solar forcing, and volcanoes, if you can predict them, or at least if they've happened before you start running your forecast, have a big impact on what's going on. And again, there's a requirement to run and initialize historical hindcasts for calibration. And yes, I say some more about that on this slide. So this is a slide about our decadal prediction system at the Met Office, which is called DEPRESYS 3. And as I said, it uses the same underlying model as the seasonal forecast system, and we initialize one member every year, which runs out for about 5 years. But we have to perform the hindcasts over a much longer period than those that we do for the seasonal forecast system. And Keith mentioned a bit about this, Keith Haynes, in his talk about reanalyses. So we have to go back for a longer period just because we're dealing with longer timescales, and we want to sample the variability in the system. Now that causes a lot of problems because we know that the observations in the ocean are quite sparse. Keith talked about approaches to deal with that using things like EOF assimilation methods, which may be better than what we're currently using. But that's not the only problem. I mean, the other problems are that not only is the observational network changing over that time, there's quite a climate change signal over that period. And because the signals that you tend to be looking for in your forecast system are smaller anyway, the whole issue of bias correction can be quite challenging. And so a lot of people have done what they call anomaly initialization instead of kind of direct initialization. So instead of starting their model from the ocean state from the reanalysis, they will knowing that will then drift away, they will use the difference between the climatology of the model, the free-running model itself, and the reanalysis to try and prevent too much drift, and then try to avoid having to do too much of a bias correction. So the NAO is something we've looked at in our decadal forecast system as well. This is a very similar plot to the one I showed before with a 0.6 correlation from our seasonal forecast system. So the question is, the decadal forecast system is broadly the same, but it's got some different aspects for initialization, for example. So does that show the same sorts of correlations, and going further back, for example, do we see the same correlations in the system? And the answer is that, again, we do get a similar sort of correlation in the decadal forecast system, so that's promising. But of course, the difference with the decadal system is we run it for longer. So we've also looked at things like what are the correlations in the second winter, which for planning purposes and impacts, as I'll talk a bit about in my applications lecture tomorrow, you know, it's much more important to know what's, well, it's probably more useful to know what's happening next winter than it is the one that's maybe just about to start and you've not had time to make preparation for. So these kind of signals which you see even in the second winter are potentially quite important. And I think decadal forecasting is really still in its infancy, but we are able to show that in most of the globe we can get skillful initialized predictions for things like surface temperatures. Actually, how much of that is coming from the initialization isn't always completely clear. So this is a difference between an initialized system and an uninitialized system. And you'll see that actually there's bits of green, so negative, and bits of positive. So it's a bit of a mixed picture, but there's certainly areas, particularly in the tropical Pacific and the North Atlantic, which are benefiting quite significantly from the initialization of the deep ocean and the surface ocean. Now, just because you see a benefit doesn't completely pin down what the kind of mechanism is, and it may be that initialization is kind of correcting for some fundamental problems in the model, rather than actually being a genuine benefit of initialization, but it certainly gives improved skill in the system. And this is an example showing some of our, I think one of our more recent decadal forecast plots showing the hindcast members that have been initialized off the ocean reanalysis, and then the forecast for the coming 5 years. So you'll see it does look, I mean, it looks pretty noisy, but in amongst there is a skillful signal for surface temperatures. And then the final time scale I'm going to talk about is climate. And this will be fairly brief. I mean, you could have, and there are whole summer schools on climate. So there's a limit to what I can really say in this context. But it's providing projections of future climate, and increasingly as full sort of Earth system models with multiple components, so not just ocean and atmosphere. Time scale kind of 10 years out to 100 years plus. Some climate models have been run for a very long time and have used in other applications like paleoclimate. And usually intermediate to low resolution, so a similar sort of resolution to those seasonal and decadal systems I've already talked about. Having said that, Earth system models with lots of complexity tend to be at lower resolution just because of the cost of running those. So mostly those would still be at 1 degree for the ocean, for example. And the very high resolution climate models that I already mentioned briefly in my first talk, and I'll come back to in a moment, are at resolutions comparable to our operational forecast system. So there's quite a range of climate models out there. Mostly, and I think Eric talked a bit about this, mostly they're still using a Z coordinate, although there's starting to be a bit more of a move away towards hybrid coordinate systems. And they require assumptions about what's going to happen in the future, so emissions, particularly land use changes, and those assumptions will be based on sort of economic modeling or assumptions about policy changes in the future, which are probably more uncertain than the physical models themselves that we're trying to use. But we have to start from somewhere. And I initially sort of put there's not really an initialization issue for climate models, but actually, if you think about it, there is quite a big problem with initializing projections of climate change if we've got a model which is drifting a lot. So I've already showed you that our seasonal forecast model kind of drifts quite a lot, and the climate models show those sorts of signals as well. And if we see drifts in the ocean temperature and salinity structures over hundreds of years, then the question is, how do you actually initialize your climate projection? You want to people often talk about kind of spinning up their climate model to a sort of stable climate state before they start their climate simulation. But that's quite challenging to do when we're sort of using present day climate forcing, for example, but we're not in a stationary climate. And it becomes increasingly important with new components in your climate system that might have very long timescales. And it may be very hard to find a kind of equilibrium state that you want to initialize your model for. So there's always going to be kind of compromises about when you stop spinning up your model and consider it useful to initialize predictions. And actually that decision will usually be made because you want to submit it to some IPCC process and you've basically run out of time. So you just have to stop even if you're not happy that the system is where you'd want it to be. And as we go on to these longer timescales, as for Decadal, it becomes increasingly important to represent the deep ocean circulations well, processes like overflows, areas of water mass formation, particularly sort of around Antarctica, for example, and the way you get interactions with ice shelves becomes increasingly important. And you want the model to have a good present day climate, and hopefully for the right reasons. And that will then help with some of these initialization challenges as well, that you won't have to run the model so long to get to a spin-up state. And typically what happens with these climate model runs is that they're submitted to things like the IPCC or to the Climate Model Into Comparison, and multi-model ensembles are used to kind of create probabilistic information about the likelihood of changes in the future. And I'll say a little bit more about some of those things tomorrow. I think someone earlier in the week already showed a plot of this form showing kind of multi-model ensembles of projections of future climate change under these various different emission pathways. And this quite sort of clearly indicates what's been seen as the sort of slowdown in global temperatures, and it kind of concerns that actually it's sort of outside the pack of these models, but actually you'll see kind of coming a bit more up to date that the black line of observations is now pretty much in the middle of the pack of what the last IPCC report was suggesting. My other slides about climate models are really looking at these two aspects of resolution and complexity. And I think that's come through in lots of what we've talked about modeling systems. It's always going to be a question about how much complexity do you have, how many coupled systems do you have, or how much resolution do you have. And as I've already said, that can be a bit of a kind of false battle, but in practice we've got to make those decisions. So there are lots of people who would say, can we trust climate projections if we know that our modeling system has got a 1 degree ocean, it's not really representing a lot of the processes in the ocean, or it's got a very low resolution atmosphere. Things like storm tracks and the hydrological cycle are all far from what we see in observed present day climate. But then there's the sort of other argument: can we trust climate projections from models that don't have any kind of land ice component, for example, or modeling of the ice shelves or other aspects of the biogeochemical system, which may become increasingly important in future? So there's always a balance between those two things. And as a result, there's been sort of two kind of parallel or potentially competing, depending on how you view it, drives to both run climate models at much higher resolution, both for the ocean and the atmosphere, and also to run much more complex Earth system models, which just by definition have to be at lower resolution. So a couple of examples of high resolution climate models. So there's a Primavera H2020 project, which some of you might have heard about, which builds on various other initiatives of high resolution models. There's a link there, but they're aiming to develop and assess a new generation of high resolution models as part of high-res MIP. And those will be the kind of resolutions we talked about. So numerical weather prediction resolution for the atmosphere, kind of 10 kilometers. Ocean resolution, certainly up to 12th degree. I'm not sure whether any of the partners in that project are planning to go even higher than that. There's been other models run recently, like the CCSM run it with a 10th degree ocean and 25 kilometer atmosphere. And these runs, I think, that have been done so far have been quite key in providing useful information for comparing with observations, and I showed some examples of this in my first talk, which help us to understand what's going on in our short-range forecast coupled systems as well, and whether there's a good driver for moving to coupling in those systems. And in general, I would say that these high-resolution climate models do seem to be showing improved mean climate in many regards and a convergence towards observations. So some examples of that, for example, sea surface temperature biases, and I've shown some examples along these lines previously, although not quite in this form, but as we've gone from these two models are both quarter degree ocean, 60 kilometer atmosphere, sea surface temperature, present day biases, to this one which has got a high resolution atmosphere but still quarter degree ocean. This one that's got 12th degree ocean with a high resolution atmosphere as well. And in general, you see improvements in the SST biases, particularly, for example, in the Southern Ocean. It's not true everywhere, but the general improvements. And related to that, there are improvements in things like the heat transports as we go to both high resolution atmosphere and high resolution ocean, which is, you probably can't read any of this, but this orange line is the one that's closest to some of the observational estimates of heat transports. And as the SSTs improve, or related to SST improvements, we see improvements in surface fluxes. So again, the eddy resolving model is of these three has got the smallest flux errors. And it's not just what's happening at the surface, of course. We see improvements in the temperature, structure, and depth, and the drifts over time. So these are some examples from the GFDL model with these three different configurations, which again have got an increase in ocean resolution and atmosphere resolution as you go across from left to right. And the temperature drifts in this system are clearly better than in the other two. And I think a move from Z-star to hybrid coordinates improves this one further. So generally we're seeing improvements in both surface and deeper ocean properties, which have a big impact for spin-up for climate simulations as well. This is an example of hydrological cycle, and this is improvements with atmospheric resolution, so going along from 270 kilometer resolution on this side to 25 kilometer in this case. And you see various aspects of the hydrological cycle change quite rapidly with the resolution increase at lower resolutions, but appear to be roughly speaking, converging to values close to observational estimates, which are what are given here on the right. Now, of course, there are uncertainties in observational estimates of these things, and it's not quite clear that things have quite sort of asymptoted, but generally speaking, we're seeing quite a few examples where the climate system with both high resolution atmosphere and ocean is performing better. And the other example is the complexity of climate models, and most of those being, or a lot of models being prepared for CMIP6 with lots of additional Earth system components. So in the UK, we've got one called UK ESM1, which has got, for example, full atmospheric chemistry, aerosols, terrestrial carbon cycle and vegetation, marine biogeochemistry, dynamic ice sheets, as well as the more traditional atmosphere, ocean, sea ice components. And we will be running that at a sort of 60 kilometre quarter degree ocean resolution, but that will be for the highest resolution simulations, and a lot of the other simulations will be done at lower resolution. I think increasingly sort of technology is coming into this, looking at ways of putting the resolution where we need it. Okay. Trying to make sure that we don't give a lot of resolution to either model components that don't really need it, so degrading the resolution for aspects of the system like the biogeochemistry perhaps in both the ocean and the atmosphere. And also beyond that, sort of grid technologies to put the resolution where you really need it, where things are going on. And that, good timing. I ran out of time to make much of a summary slide, so my general sort of thoughts were there's been lots of progress in seasonal and decadal prediction over the last 5 years, I would say. I think there have been quite significant advances driven by both the move to higher resolution and improvements in initialisation as well. And I think it is looking like there's actually a lot more predictability on these timescales than perhaps a lot of people previously thought. These high resolution climate models have been very important for understanding what we might want to do on shorter timescales, and they do help to provide more confidence that the models are actually representing what's going on in the current climate, and therefore we would have confidence in projections in the future. Of course, the kind of thing that goes along with that is they're very expensive to run, so it's difficult to run ensembles of those, and so difficult to come up with probabilistic assessments of what might happen in future. And as a result, those are complemented by lower resolution models, which have more Earth system components as well. So there we are. Thank you.
Thank you, Chris. So thank you for giving 3 lectures. It's a lot of effort, so we appreciate it.
There's another one yet. There's one tomorrow.
Yeah, you had 3 in total, no?
4.
Ah, it's 4, it's true. Yeah. Oh, okay. So you are the winner. So any question for Chris?
As I say, I'm not the expert on this, so if other people know the answer more than I do, feel free to contribute.
One of the things that Mike sort of focused in on yesterday was how important sort of these pulsing sort of stochastic events and the strength of them was in seasonal forecasting.
Yeah.
So it's like, how do you weight your stochasticity to sort of try to recreate that?
Yeah, so I don't actually know the details of the stochastic scheme that we're currently using, and as I say, it does seem to have been a bit. Well, there's a possibility that it's having impacts that we didn't want on the signal to noise in the system, which again I don't think we really understand. Yeah, I mean, I think when Mike was saying that, it sort of made me sort of think actually how much of that what you want to do is dependent on atmospheric resolution as well. And whether we have done tests with higher atmospheric resolution in our seasonal system and not seen that much difference, but how that's kind of playing into the kind of stochastic aspects of the system, I don't know.
I've got very general question. Why spatial resolution of the grid for ocean models is measured in fraction of degree, while for atmospheric it's fixed in kilometers? Thank you very much.
Yes, I mean, I always translate the atmosphere ones into kilometers, which are just sort of roughly a sort of mid-latitude resolution value. So I think they're only ever approximate. I mean, some people would translate the ocean resolution from, some people would talk about 12 degree ocean as being whatever resolution that is, 12 kilometers. But yeah, I mean, I think we're just used to referring to things like that, and particularly in the NEMO community when we're using these tripolar grids, and there's quite a big variation in resolution in different parts. That's kind of the easy way. I guess most of the time, most people would talk about atmosphere resolution using sort of N216 or T6 whatever. So depending on whether it's a kind of spectral grid or not. So they're just different conventions. I don't think there's any fundamental reason behind it.
Okay, thank you. Thanks again. And so we close the session. So have a nice evening and see you tomorrow at 9